A baseball team plays in a stadium that holds 54,000 spectators. With ticket prices at $10, the average attendance has been 38,000. When ticket prices were lowered to $8, the average attendance rose to 42,000. Find the demand function. So that is the price P as a function of attendance X. And we're going to assume it's linear. It's part A. And then part B asks, how should ticket prices be set to maximize revenue? So first step, understand the problem. So part A, they're telling us that we want the demand function, which is the price in terms of attendance. And they're telling us it's linear. So if you look at this problem, we want price to be a function of attendance. So notice that if we're finding the equation of a line, we're actually being given 2 points here. We're being given when attendance is 38,000, price is 10, and attendance is 42,000 when the price is $8. So we'll get our linear function from that information for part A. Then part B asks how the ticket prices should be set to maximize revenue. So we're going to think, okay, what's revenue? It's the total amount of money made before you subtract costs. So in this case, it would be the price of one ticket times the number of tickets sold. So we'll be using that price function that we found in part A and then multiplying it times the number of tickets sold to get our revenue function. And that's the function we're going to be maximizing. Very helpful in this problem. So the next steps introduce notation. That's pretty easy. So we can say price is a function of the attendance X. So P of X is our price, X is our attendance. So that's the number of tickets sold. And then our revenue is going to be a function of price and attendance because it's price times the number of tickets sold. So it would be price times X. So our revenue is actually going to be a function of the attendance. For part A, since we need to express R in terms of price, we need to find price, which is part A. So, like we said before, we're actually given 2 points on a line since we were told that P is a linear function. And we're told that the price depends on the attendance. So the price is the dependent and the attendance is the independent, or the X in this function. So just using the 2 points of on a line, I get P of X minus 10, so I'm using this point, equals the slope times X minus 38,000. And simplifying, I get this line. So that's telling me that the price is related to the number of tickets sold by this linear function. So now we look to part B. How should ticket prices be set to maximize revenue? Well, we know that our revenue function is the total amount of money made, right? So that's the number of tickets sold times the price per ticket. So that would be X times P of X, which was our demand function that we got in part A. So this is our revenue function. We now want to think about, we need to maximize that. And we do have a closed interval because the stadium can only hold up to 54,000 people. So we're going to use the closed interval method to find the maximum value for this revenue. So to find the critical numbers, we take the derivative of the revenue function and set it equal to 0. And solving r prime of x equals 0 gives us a value of 29,000. So since I have a closed interval, I'm going to use my revenue function and check the value of the revenue at 29,000 and also at the endpoints of that interval. And when we evaluate the revenue function at 29,000, we get 420,500. When we evaluate the revenue function at 0, we get 0. And when we evaluate it at 54,000, which is the right end of our interval, we get 108,000. So an attendance of 29,000 is what maximizes revenue. So remember, we were asked for the price that would maximize revenue. So if we go back to our price function or demand function and evaluate that at 29,000, that tells us what price to charge to get an attendance of 29,000, which in turn will maximize revenue. So when we evaluate our price function at 29,000, we get 14.5. So that means that they should charge $14.50 a ticket to maximize revenue. In summary, there's really not much new to say here in this lesson. It's more just applying what we've learned. And as usual, the hardest part of these problems is coming up with the function that you're trying to maximize or minimize from the description in the problem. Following these steps are a good guide, and whenever possible, drawing a diagram is helpful. And that's it for optimization.